Okay, let me do that. I'll put it on a private channel. It doesn't matter actually. Okay, so today, so the focus is on the infotainment. So we did our research and trying to understand, what is required by companies that are doing infotainment. The goal of infotainment is experience and safety. So improve the driving experience and increase the safety. Now, there are a lot of components in entertainment and infotainment. There's the audio video interface, there's the screen where you have a touch screen, you have buttons, you have voice command, you have a lot of things. Also, they have to connect to the autonomous driving systems, like they connect to the cameras, they connect to the artificial intelligence, they connect through 5G or through, through Wi-Fi to like the pedestrian, to the pavement or to the line markings. They have the telematics systems. They connect to smartphones because they have an app in the smartphone that says, change the temperature, for example. And of course, lots of sensors, humidity sensor, temperature sensors, and all of those things. So this is in a nutshell, what infotainment is all about. Okay.
Yeah.
So probably the most advanced infotainment system is in the Tesla car. They got that big 17-inch screen. So that is probably the most advanced infotainment system in the market today. Oops, what happened here? Okay. So the parts of an infotainment system is there's the integrated head unit, which is on the dashboard. You see that big, like the 17-inch screen I was talking about. It has that unit. So that's the first one. There's also these new ones, which I think the Prius had, where you were displaying the information, like the instrument panel onto the glass, onto the front window. So you have something like that. And of course, there's a lot of high-end DSPs and GPUs that they're using to support multiple displays. Because now you can have a display in the front, you can have a display in the back, you can have a lot of things. And now there's also a lot of questions about which operating system to utilize for this one. So this operating system is also analysis. The Drive PX comes default with CAN and Ethernet, but there are other chips with other protocols like MOST and FlexRay and things like that. And of course, there are also connectivity to GPS, Wi-Fi, 5G, Bluetooth, that toll road connection. So there's a lot of those kind of connectivity or wireless things. And then there's sensors. Proximity sensor is probably an important one, showing how close you are to, say, a person crossing the road or the car in the next lane to you. Those kind of sensors. And of course, the last one is converting what we are used to with the static to more of a digital display. So these are all the different parts of an infotainment system. So if you look at the block diagram, typically what you have is a display controller, and then you have a series of other processing controllers that then are sent to the different types of display. So you can even have a rear seat entertainment system as well. And different things, your Bluetooth for your audio, you can have the 360. So a lot of cars now have a 360-degree view around the vehicle, things like that also. And of course, the parking cameras as well. So this is kind of like an early version of an infotainment. It doesn't have all the functionality, but this is kind of gives you an idea of all the, the input on the left side and then the output on the right side. Okay.
Yeah.
Now, iOS, you connect the gateway. There's an infotainment system right over here with USB connections. And then you have the network that connects everything else in the car. Anything from audio sound systems to the lighting, all of those can have a control right in the infotainment. Even the rear view adjustments can be done now with the infotainment. So almost everything gets connected. So it's a pretty big, matter of fact, I was reading somewhere, they said it's about $30 billion is the, $30 billion is the infotainment system market. So everything can be connected. It can either be a control or it can be a diagnostic with feedback. So both of those are happening. Okay. So now, if you take the full infotainment hardware, this is the slide I took from Synopsys. Okay. There's a lot of interfaces going around, a lot of processing like CPUs, there's sensor control, there is graphics, there's even DSPs, there is security devices, there's all the network interfaces. So there's a lot of interfaces, a lot of memories, processors, even like on-chip memory, things like that also that are part of the whole system for infotainment. Okay.
Yeah.
So a lot of devices, just be aware of that. So, maybe the thing we're looking at with Panasonic might be just that one small model, but it could be that Panasonic may be asking us for all these other devices. So we just need to be prepared if they ask us for any of those other ones.
Yeah.
Okay. Now, the main problem that I see is infotainment systems have to be really cheap. You cannot, oversize the system. So low costs, low energy consumption, and maximum number of sensor integration. Because more number of sensors you integrate, there is more safety features, there is more driver experience. So it's low cost, low energy, maximum sensor integration. So to really be able to test something, you have to run a large number of use cases with minimum amount of hardware integration. So you want a lot of these systems, because the space is very small, they want to use the most highly integrated chips. That's why the Drive PX is very popular, because it has the GPU, has the processor, has the CAN and Ethernet, has a lot of those integrations already done. So a single chip can replace about 5 or 6 chips in the board behind the head-end systems. The other one that I was reading about was they don't want to build their own ASICs. Most times they just want to use or reuse and off-the-shelf components and build up the system, because apparently infotainment life is very small. Within 6 months or 9 months, they have to put a new version out. So there's a constant, change in the architecture or in the design of these systems. So from a hardware design challenge, the biggest thing is bandwidth versus latency. As I keep increasing the latency, how much does my bandwidth fall off? So I need to keep getting the memory access for the bandwidth. So that's the most important thing. The other one is looking at how much of processing time it takes on the ARM. Typically, all of these are ARM or Tensilica or ARC. These are 3 embedded processors they're using. And so they're looking at, delay for CPU or DMA, because DMA is where I have all these interfaces and I'm transferring data over to the external DRAM. So they all use DMAs. So what is the processing time associated with that? The other big thing is that, for the display controller, say the display controller updates every 33 milliseconds, all the other processing for the data must be done before that 33 millisecond slot. So we have to look at the timing deadline for all that processing. This is the most important consideration. All of these are enabling this one to make sure that all of them complete within the timing deadline. Okay.
Yeah.
Now, the peak power, this was another thing, because these entertainment systems should be able to tolerate any temperature, be it in Saudi Arabia or be it in Finland. It should handle any temperature range. So the peak power, starts increasing the cost of the system, because the higher the peak power, the higher the the cooling costs and things like that. So it's very important to do the to make sure the peak power is kept low. It's a very important consideration. Now, the models I've still not integrated the power. I will do that in the next day or so to add the power consumption to the model also. Right now, I just have one example showing the power for the GPU, but I'll have the power integrated for the whole system. Okay? The other one is the cumulative power. How much of power are we consuming over time? Because that tells you how much. Now, most of these are electric vehicles, the new ones. So, how much of the power are we consuming over a time period? So, if I'm doing, say, my, like watching a movie, how much is the power consumed for watching the movie? So, that kind of a consideration is also very, very important here. Okay. So, one of the things, spelling is wrong here. Let me change this in a second. Now, one of the things that I did was I tried to look at, how people are doing architecture exploration today with infotainment. There's really three options. You can use a spreadsheet, which looks like Panasonic is also doing. That seems like the most popular mechanism. So they don't look at concurrent operations. What they do is they line up all the traffic from all the sources, and then they say this is the delay in each of the blocks that they go through. And at the output, they say here's how much is the latency, and here's how much is the throughput. Throughput and latency seem to be the most popular reports that they want to generate. Okay? So they look at all the traffic, they add it up. What they don't do is, one is obviously analytical model approximate, but the bigger thing is they don't take into consideration what happens if two of this traffic comes to a single device, like say a bus or to say a common DMA. One has to finish, then the other has to finish. So that buffering type processing is not taken into consideration. So the range may be very high. Your lowest thing is that, it's always available, goes through, or they can say, every one of them has like so much of buffering, has like this big delay. So they end up having this huge probability range. Either it's like, like absolutely best case, which will never happen, or absolute worst case where it never happens also. So, like if you're going to design for that range, it's going to make the product very expensive. Okay. Prototyping. So most people right now are building prototypes to do these kind of architecture analysis. So they take a minimum set of combination, either using the previous generation design or taking the previous generation, but replacing with the next generation with the same chip. So you use Drive PX, now let's do Drive PX2. Or use an NXP chip, use the next generation NXP chip. So that's kind of what people are doing. The problem is, fabricating it and all of those things take a long time. It can take up 3 to 6 months. By that time, chip generations have changed, requirements have changed. So now they have to either redo it or make some assumptions by taking the values out of the prototype and put that into the spreadsheet. That's what most people are doing right now. So with system level modeling, the advantages. First is, you can create these different models and you can have any number of variations of these models. This is very important. It's not just a single variation. If I have 20 variations of my infotainment, I can have 20 variations of the model. So that's one thing. The second thing is, you can start off with a stochastic model, which is more of a traffic model, identify where your bottleneck is. Then you can start moving into different levels of abstraction. So you can, based on your requirement, you can start putting them down as, you can start, like saying, okay, like I showed you, you can have one which is all periodic, then move to a burst mode, then move into like a cycle accurate mode with the processors and GPUs. So you can start, integrating more and more details into the same model. So if you decide I just want a quick analysis, I can use a traffic model. If I want a very detailed analysis, I start putting the processor and things like that. Two advantages. One is, the more traffic models are used by early systems engineers or research engineers, but then the product designers may need the more detailed ones. So same model, same traffic, same interfaces, same displays or IOs, all of those can be retained and just the internals can be modified. So this is an easy way for you to to go from one level of detail to another level of detail, or one level of abstraction to another level. So this is what I found, based on my research on the web to see how people are doing it. Any questions?
No. Yeah, it's okay. Okay.
Okay, so this is the minimum set of library blocks that we need from VisualSim. Obviously, we need the traffic blocks. We need the system resource and the queue blocks. I think you're going to eventually need the networking library. As of now, most people are saying, oh, we just take the traffic from these different interfaces. We don't actually model the entire network, but could be in the future they may want to model the network as well. So that's why I've included the networking library, but as of now, maybe they won't need it. Hardware. Initially, they use system resource and queues for hardware, but then later on, they can start using the processor, memory, devices. Not only would they use like the inside of the drive PX, it's an AXI bus, but they can connect to say a PCIe on the motherboard and connect to other devices on the motherboard itself through the PCIe. So that's one possibility that you might be using some of the other buses. The hardware part, this part is fairly easy because you can connect up the thing. The difficulty is really in describing the software behavior. What are the applications that are concurrently running on the system? Defining this is the biggest challenge. So what I did was I put together this model. I think it's this one. Let me check. Yeah, this is the one I put together. So what I did was, I kept the hardware platform like this. So I have the Ethernet, the CAN interface, multi-core RAM, the GPU, and the display controller. So, and then I have the AXI bus, the DRAM display, no change. But now I created the behavior flow here separately, meaning that, I've got two different applications. Each one does a sequence of things. This part is all done in the, is done on the multi-core ARM, while this one here, these are to the GPU, and this is to the display controller. So I can kind of describe different applications. In this case, I've connected them up as two independent, but for example, what I can do is, and like for example, here I have an enable for the display and GPU, but what I can do, for example, over here, I can connect them to a single flow and send them through. So rather than them having two independent flows, they can, both of these are required, or I can feed them into a single flow and continue down. So I can have different kind of combinations of these applications built up here. This, I think, is a very important thing, considering, like when you start getting into more details of what is the sequence of things my software is doing, okay? But we're not going to talk too much about that right now. Today, the focus is more of the simple traffic model type analysis. Okay. Now, a variety of statistics is what I was seeing that people wanted. So I picked up the ones like latency, which is for each device, like for CAN, Ethernet, ARM, GPU, display controller, what was the time it took for each one of them? The other one was looking at buffer usage. So right now, the buffer I'm focusing on really is the bus buffer, but we'll start looking at other ones later. The other one was looking at on the bus, how many entered, how many exited, and any of them dropped. So this was an important one. Then looking at utilization, especially on the memory utilization, the memory throughput, and then looking at power. These four I'm not going to talk about today because we haven't updated the model for power. But that is something that we will do after this and show you some of the details later. Okay. So these are the statistics I would say we want to focus on today. Any questions?
Okay.
Okay. So we started with, hang on 1 second, sorry. Something got deleted here. Okay. So the model I constructed was this. So I have two packet generators, one's a CAN and one's an Ethernet interface. Both come through the AXI bus and they go to the DRAM. The CPU and GPU, they have interaction, they have read and write to the DRAM, but these are only writes. The interfaces are only doing a write to DRAM. The GPU and CPU are doing reads and writes to DRAM. And the display controller was unique. It first does a read from the DRAM and then it writes out to the display IO. So that's the sequence of operations. Both of these do reads. This one does reads and writes, while this one does first does a read from the DRAM, gets the data, and then it writes out to the display controller. So that's the basic system that I've constructed. Any questions?
No.
So to give you an idea of what the system looks like, so this is the system model. There's a lot of parameters, but just important ones are, you know, I have the CAN bus rates. So this is the Ethernet. I have a start time, and then I have a minimum and maximum range. So something like in this case, the Ethernet comes between like I generate a random number between 8 and 12 milliseconds. So every packet does not come out periodic, but it comes in a range. So between 8 and 12 milliseconds, the time range between different packets. I'm using the maximum size for the CAN and Ethernet packet. So it should be 1512, not 1522. Okay. And then of course, you know, I've got the ARM reads, ARM writes. So that's my read rate and my read size, write rate, write size. Similarly, I have GPU read rate, write size, write rate, write size. That's my GPU. And then for the display, I've got a, you know, it's like an enable at 33 milliseconds. That's what I have over here. Yeah, go ahead, Jimmy.
Can you make the graph larger so we can read the parameters?
Sure. Let me make it full screen. Can you see it now? Is it clear?
Well, no, yeah. Got it.
Yeah, it's better.
Okay. So what I'll do is I'll just make it a little more bigger so you can see it better. So if you look at the range of parameters, again, the CAN, I have a min and max range. Similarly for Ethernet, I've got a fixed size for packet size. These are my read rate, read size, write rate, write size. Then that's the display rate for the display controller. Same thing for GPU. And then I've got bus width, memory width, frame rate, things like that. Okay. So how is this utilized in the system?
Deepak.
Yes.
Okay. What is ARM read rate? What is?
I'll come to that. I'll explain what each one is.
Okay.
Okay. So that I just wanted to show you what were the parameters. Now, the reason we have given lots of parameters is because we believe that the user will be doing a lot of experiments. Okay. So that is why we have a lot of parameters. Now we can discuss it and see if you want to reduce these number of parameters, and we can do that also.
Okay.
So what we have done over here is we are using a traffic generator for the reads. So we're saying that the read rate in this particular case is we have a read rate of 10 microseconds. So what that means is every 10 microseconds, a request is going out. A read request is going from the ARM to the memory. Okay. Similarly, for the write, I have a write rate. So what is the write rate over here? Every 25 microseconds, I'm sending a write request to memory. Okay. Does that make sense? So read is every 10 and write is every 25 microseconds.
The value is the cycle. Is the cycle? Cycle is
yes.
10 microsecond. each 10 microseconds.
Yes.
Okay, 10 microseconds to read from the memory is 512 bytes.
Yes. Yes.
Okay. Yeah.
So
Yeah.
every 10 microseconds, I'm reading out 512 bytes. Every 25 microseconds, I'm writing 512 bytes.
Oh, okay.
Similarly here, every 100 microseconds, I'm reading 1024. Every 250 microseconds, I'm reading 1024.
Okay. Yeah.
So this model is very simple. Here, I have my minimum and maximum range. In my device interface, all I have is a write and my Ethernet packet size. That's all. And it's going to a DRAM. Nothing else is being used. Okay. Similarly for CAN, writing to DRAM and a scan packet size. That's it.
Okay.
So traffic is being generated at a certain rate, and then it's the Ethernet and CAN. It's going the size and where the destination is. That's all.
Yeah.
Okay. Now, for the ARM, this is a little bit different in the sense that I have the ARM, so I have a read rate and a write rate over here. Now, this one here is a hierarchical block. The reason is, oops, I have the read and write that I have to combine into a single flow. Okay. So here I'm setting that is a read, this is the size, and that's it. Similarly over here, I'm setting the read. Oops.
Right.
Yep, I was making changes today. Sorry about that. Good catch. Extra chocolates for Tanaka-san. So here, so I put a write, and then I have a write size. And then this one here again, just has a DRAM. So, depending on which flow it comes from, it reads in and it goes through that thing. That's all it does. Okay. Similarly for the, for the GPU, it looks identical, no difference. So I have a read with the GPU read size. Let me see if I made the same mistake here. Write with the GPU write size. Sorry, I made the same mistake in both cases. Here also no change, just saying it's going to the DRAM, nothing else. Okay, and now the enable display, it has the frame rate, which is 33 milliseconds, very common. There's one difference inside of this. Here what I have is I have the display. So say display controller, go to the DRAM and there's a read, the frame data size, which is a parameter at the top level. It goes through the flow here. It goes out from here. It goes through the flow, goes to the DRAM. And when it comes back on this flow here. What I'm doing is I'm sending it out again to say I want to go to the display. So it goes out and then it returns again, and it says I'm coming, like I'm going out again. So first step is I'm going and reading, which is right here. I do a read of a data size, and then when I get it back, I'm doing a write. I'm converting that into a write, and then I'm doing a write over here. So I'm writing it out to the display. The destination is a display. In fact, I think I missed one more point over here. So I'll do an A command. I should do this as a write. Again, I missed it out, sorry. So first one is a flow, does the read, comes back, does a write, and when it's done, it comes here and it says, okay, I'm done. Okay? Does that make sense?
Yeah.
So hopefully this is a simple model. Right? So now when I go ahead and run the simulation, I'm just going to run it first and see if there are any errors because I created all of these things. So one of the first things you're going to notice, and I'm going to make this nice and big so you can see it well, is that you will see I've got the ARM, GPU, CAN, Ethernet controller, and display controller all listed over here. And you can see the range is quite high. So if I take, like, say, the ARM processor, you can see it's all the way from like 100 microseconds down to, to maybe about maybe about 1.5 nanoseconds. All the way from 1.5 nanoseconds goes up, and even there's some here that are even at 200 microseconds. So for example, in this particular case, see at this point, at like, what is it, at 8 milliseconds, I'm getting multiple tasks hitting at the same time. So my GPU and the ARM are coming in at the same time. Plus, I also have the Ethernet interface coming in at the same time. So if I zoom into this region over here, you'll see I have the Ethernet, I have 2 ARMs, and I have 2 GPUs coming in exactly at the same time. Okay? So I get this huge, I get these huge spikes. But also there's also some mini spikes over here. I see this, then you'll see also there's some spikes over here. See like this one over here. So there are some differences as well that show up. Also, if I zoom into this region over here, you can also see that there is some slight changes even with the Ethernet and with the CAN bus. They're not fixed. Okay. Now, to understand what's happening, this is the parameter that's kind of important. Okay. This is the bus traffic. Show you what's happening on the bus. I'm going to go up and you can see, so master one, hang on. I'm going to move this to the side over here so we can see which one's master. So master one is Ethernet. You can see it's writing out at this rate. Master two is CAN. It's writing out at this rate. Then you can see master four, which is this block over here. You can see the read is 51 megabytes per second, write is 20. For the GPU, which is this one over here, going to this one over here, it's, I'm sorry, this interface over here. The GPU's got a read of 10 reads and 4 megabytes of writes. And of course, this is the read and write on the master. And you can see the slave gets 61 megabytes of read and 24 megabytes of write. Now, here's the thing that is key. The read and write has buffering on the slave side. So on this slide, there's a buffer of 3 on both of them. Okay? So that's one of the reasons why you see these peaks here. The peaks are related to this threshold right over here, these two. So what I can do now is I can change this where I can, let me start with just the bus, okay? I'm going to change this read and write threshold to be 2 and not 3, okay? Same design, no difference. But you can already see the spikes over here. You'll actually notice the profile looks a little bit different. It's not exactly the same. So like notice over here, these things change also. Notice here, look at this. The display controller is way over where it should be. It's at 200 microseconds. Look at this. Actually 225 microseconds. So which means that the display controller is not getting its preferred bandwidth right here. If you notice earlier on, it was right at the bottom. Now it's right on top over here. And all I did was I modified what was the buffer on the slave side over here. So luckily there's no overflow, but you can see over here, I'm still getting the 61 and 24, but this one here has been, the latency on it has pushed up. That's because the thing is, if you look at the slaves now, earlier on you had 3, now you're having 2. So if I go down here to look at my master 9, you notice I had a buffer. Earlier on there was no buffering. There was no buffer occupancy. Now I actually have a read and write buffer occupancy on my, oh, that's wrong also. master 9. I have the buffer occupancy right over here. Okay. And you'll also see that the slave, even this latency has increased a little bit. Okay. Again, there's still 86 megabytes, no difference, but then the latency has increased. So that's on that side. Now, what I can do is I can change this one. So I can make this go at -4, which means I now, rather than doing 8 milliseconds, I'm going to move it to 800 microseconds. So it's going to run much faster, almost 10x faster, for the same design to see what's happening. Big change. Look up here. You wouldn't expect this because you were seeing spikes here, right? Even though I increased it, no spikes over here. Any reasons? This one has gone up, but we were seeing spikes over here. The spikes are not there. The reason now is there is no overlapping of the Ethernet, except for this one point here. There's no overlapping of the Ethernet with the GPU and the ARM. Okay, so as a result of which we're able to get we're able to improve the performance. So even though we increase the traffic rate on the Ethernet, because we're not getting any overlaps, we're actually getting a slight increase in the throughput as well. Similarly, like I can start putting, like I can increase the data size over here, for example, on the GPU, not on the GPU, I'm sorry, on the frame data for the thing, for the display controller, I can increase that. Probably not. Yeah, that's okay. We'll see what happens. So even though I increased it, the latency has not increased significantly. So what this tells me, this is an important thing here. Even though I made it 10x larger, I would expect that my latency would be much higher. But notice the spike over here, right? Even though I increase the increase the size of the data by 10x, my latency has not increased at all. Any idea why? Because go ahead.
Deepak, does that mean the XC bus is never congested?
This is the reason. The reason that you're not seeing, initially the value was very low for the display controller. Then it came up to this level, but now it has not increased, right? Even though we increased the data size, the reason is most of the latency is on the buffering. The latency is not is not for the transfer time. The latency is on the buffer. That is the reason you're seeing that even though I multiplied it by 10, I don't see an increase because it didn't matter. The transfer time is so small. Most of the time is related to the buffering. Okay. So you'll actually see here, notice the data. Yeah, go ahead.
Where physically, where is the buffer?
The buffer is on the interface on the port here.
So everyone has a different buffer, or they all share?
Yes, they all have. So these are the master request threshold. Each one has its own buffer. So for example, which we were 5, right? 1, 2, 3. Yeah, let's do this. 1, 2, 3, 4, 5. Let me change this one to only 2. Right now, I allow for 20 packets. I'm going to change it to 2 packets. Let's see what happens now. Notice here it's dropped. Remember we were at like somewhere over here. Notice this is dropped. So what is happening now is, oh, I still managed to send it through, so I don't have too much of an overhead. But let's see. Yeah, it's not much of an overhead. But let me do this. Let me increase this to say 3. Read and write to 3. And I'll keep this at 20. I'll go back to that. Now let me rerun this whole thing again. Notice you don't see the GPU here anymore. You see it? So the master buffer is not so much an overhead. The slave buffer is where the overhead is. Accessing the memory, that's where the overhead is. You see it? Does that make sense? Tanaka-san?
Yeah. I'm sorry. I'm sorry. I have the basic question.
Okay.
Okay. What is the bus threshold?
Which one? Or threshold?
Yeah.
Oh, it's
What lead threshold and the right threshold.
Sure. The threshold is essentially the buffer size.
Buffer size means
yeah.
What is the 3? What is the number of the 3? What means?
3 is 3 packets.
Oh,
or
packet.
3 transactions. Yeah,
Number
3 transactions.
Oh,
yeah.
okay.
See, we have it over here. So transactions are in byte size, but we're using transactions. It's more efficient. So you can say, 3 transactions. So that data sizes are fixed, right? So 3 sign. So on the slave side, we have 3 transactions of reads, and it's a separate. They have separate channels. So 3 buffers for the read and 3 buffers for the write.
Okay, threshold means this bus. Okay, this bus has a number of 3 packets of the buffer.
On the slave side. On the master side, each one has 20.
Okay, master, okay.
Yeah,
master.
This is the master side. That has got 20. Slave side has only 3 and 3.
Okay, slave. Okay, slave means okay, this architecture DRAM on the display.
Yes, exactly. So each one has 3. So there's 3 over here and 3 over here.
Okay, okay.
So each slave has 3 read buffers and 3 write buffers.
Okay.
And
okay, please.
I'm sorry. I think I have the same question like Tanaka-san has. So read threshold, write threshold, that is the parameter of the axis bus. So
yes.
if we click the bus and look at the document, so it's in the document.
Yes,
that right?
That's correct.
Okay.
If you go in here, library documentation, if you click on this, click on interface and libraries, click on Amber, axis, open a new tab. See here.
Okay.
That's the three parameters right over here. Okay. That's what it is. Okay. Now, there's another parameter that we have over here. I'm going to details now. Another parameter we have over here where I can change this threshold. Like right now, if you notice, I said it's 3 packets. But I can change this to where I can make it in terms of bytes. So if I set this parameter to false, right now it's set to true. If I set this to false, then what happens, I can set it to number of the data size. It takes a field called A bytes. Go back here. Oops. There's a, We update this field called A bytes. It takes the size of that and then it measures the threshold. So you can either do it as packets or transactions, or if you set this to false, it becomes bytes. But I would prefer just keeping it as transactions, because unless you're a very detailed hardware implementation engineer, you don't want to deal with bytes. You want to deal with transactions. Okay.
Okay, and one question is, master request threshold. Threshold can define each bus master.
Yes.
But the flip side, the little threshold is only 3. It can't define each thread.
No, because that's how the AXI definition. AXI definition allows for each master to have a different threshold, but it's same for all the slaves. That's the reason.
Okay.
Of course, we can try to. There's not a lot of interaction. Only in a few places there's interaction, but I can make it a round robin. So rather than using a fixed priority, so I assign a priority for each master at the slave. Like for example, we only have 1, right? So this is the kind of the higher the number, higher the priority. So this is the order. So I can do it, but I can also make it a round robin, or I can put in my custom algorithm. But for Panasonic, this will not be a requirement. This would be more of if you're doing SOC IO next or Fujitsu or someone, then maybe they might look at this. But round robin, if I set this, you won't notice. In this case, you won't notice much difference. But if there's a lot of overlap, you will notice some difference. I mean, there is some very minimal difference, not a whole lot. Little bit, there's a little bit difference, not 100% the same, but because you're using a different, arbitration scheme. So notice here, this is the orange ones over here. Oops. Come on. There's my, sorry, 1 second. 816, 10. So between these two should be 133, right? Right over here. Okay. Somewhere over here is the orange one, which I can't see now. 33, let's look around here. Oh, here we go. You can see this. So it's only 350. This is the display controller. That's the threshold for that one. So you can see that earlier on it was much higher, but now all of them get equal priority. So you can see that they're going in a round robin loop. So that's the thing. Again, it doesn't change the DRAM throughput. Now, one thing that does have a big impact, I can do 1136 or 1137, which is the DDR3, and make this 8 bytes. So this is changing the memory. I put a cheaper memory. You can see that not a whole lot of difference because the memory is not utilized that much. It's still at that 0.35, but there's a little bit of difference here. See, there's only that point. At that point, there's a lot of multiple things are acting at the same point. Multiple requests are coming in at the same time. So that's the reason. You can see the CAN bus, the ARM, then there's the GPU, they're all coming. So what I can do to make it really, really look bad I can change this. I can change the ARM read to -7. And then I can change the, yeah, I can do that. And I can change the GPU read to also -7. So you can see how the whole thing has changed now. See, the range of this is much higher. Actually, if you look at these, look at this, it's not flat. You can see where the Ethernet is also changed. I'm sorry, the CAN bus has also changed. Okay. And notice also it's taking a lot longer to run. Oh, here we go. You can see this, lot of activity right at that one point. So at this point, there's significant buffering. So a lot of the ARM data is being, packetized right over here. So a lot of activity right there, even at this point. So you notice this one also, there's a spike up over here for the GPU. And it happens at these regular intervals. So this is when the display controller is acting. So 33, 66, 99. So that's when the display controller comes on. And that's when you see these spikes. So display controller is essentially blocking off everything else. So the amount of data it has to transfer.
Okay.
Deepak, is there a way to resolve the problem when display controller is active? It looks like the problem is quite serious.
Yes, it is. So the display controller gets the highest priority because you don't want to see, the thing is the driver experience is what time the screen gets updated, right? So if it does not get updated at 33 milliseconds, like my daughter, if she turns on Netflix, it doesn't come on immediately, she turns it off and goes to Amazon Prime. No patience. Same thing. If the Spotify does not come up on our display screen on the in our car, immediately she gets upset and goes to some other channel. So the display controller part is the most important thing. It has to show up. Okay. So everything else you can you can delay except the display controller. Also notice now we went from about 86 to we're now at 587 megabytes. Now what I'm going to do is I'm going to increase the data size over here even more to try to cause a problem on the DRAM side as well. See, the main idea here is, the ARM and GPU rates changing is really all about, it's all about, how much more processing can I do? How many more things I can do? Like going from like a 1080i versus a 4K display, right? The processing is significantly changed. So allows me to look at, what happens in those different scenarios when I change some of that processing. How does it impact my system? Obviously, this is sending a lot more data. If you look at the simulation performance, you will notice that the earlier one took only about 29 seconds. I'm sorry, not 29. Yeah, the earlier ones were taking 29 seconds, but now if you take the new models, they're taking 183 seconds because there's a huge amount of increase. We've done almost 100x increase in the amount of data, but the simulation performance is not 100x. It's only about 5x slower. It was sending 100 times more data, but simulation performance is only about 5x slower. Obviously, if you don't want to stay for so long, I would say reduce the simulation time also as you start putting in more data. Any other questions? Sounds interesting, Tanaka-san?
Yes, yeah.
Easy to understand?
I think so.
Okay, good. If sales guy can understand, engineer can understand faster, right?
Customer can modify the the many parameter. Ethernet speed and packet size and the processing cycle or the buffer.
Yes.
Okay.
DRAM size. So this is the first model.
But I think bus model has a lot of parameter because of this is a AXI specification.
Yes.
If the customer if customer has knowledge for AXI bus, they can understand easily to your it's the architecture name for the read threshold, the write threshold. I don't know.
Yes.
That. Customer can understand easy for the many parameter. Can customer easy to understand this model AXI bus? If customer has a knowledge of AXI.
Yes.
Okay.
So important thing, there are only 3 parameters the customer should modify. Only 3.
3?
The first, only 3. AXI speed, which is the bus speed.
Okay.
The width of the bus, and these 3. The read-write thread, the buffer sizing.
Okay.
Speed, width, buffer sizing. That's it. Nothing else.
The master request threshold is.
Yeah, that's what these 3. The 3 thresholds: read, write, and master. 3.
Okay.
So speed, bus width, thresholds. That's it.
Okay.
Nothing else. No other changes.
Speed is megahertz clock.
Yeah, speed megahertz, exactly. Whatever the speed, whatever the bus width, and the 3 thresholds. That's all. They don't need to worry about everything else. They can ignore all the others.
And I have a question about the actual AXI bus. Actual AXI bus can modify the 3 parameters.
Yeah.
Buffer size and threshold and bus radius and the clock. Maybe clock.
Clock, yes. Bus width, no. They cannot modify bus width. Bus width is fixed, but buffer, they have some flexibility. They can modify a little bit. But also it depends on, if I move from one, they might have many variations of the chip. So if I move from one variation to another variation, it'll also be different.
Okay.
Speed depends on the chip. That one cannot be modified. So so it depends on, if I go from one chip to another chip, it'll be different. But for one chip, it'll be fixed.
Okay.
User cannot modify it.
Uh,
But the user can modify the memory because that's an
Yeah.
external device.
External. Okay.
Because they can buy, I can buy a DDR3 at 1137, or I can buy a DDR4 at 2400. I can buy different DDR chips.
Okay.
That is decided by the systems engineer.
Yes. Yes. Yes.
And these, again, Ethernet interface, CAN interface, that depends on your design. So these four is important from a design standpoint. These here are, like just providing information to say that, I'm going to be processing so much of data. Again, software engineers will have this information, GPU and the ARM rates.
Yeah, maybe customer, can, it depends on the application.
Yes.
Software.
Yes.
Yeah.
Exactly. That's correct.
Yeah.
Right.
Software engineer can set the read cycle and write cycle and
Yes,
okay.
That's correct. So this is one version of the model.
Okay.
Deepak,
yeah, go ahead.
Can I ask that we try out something on the memory side, say the access time?
I just did. Sorry, wrong model. Oh, there we go. That's what I changed this from 2400 to 1137. Not a whole lot of changes because when I look at the stats here, wrong stats. See, I'm only consuming about 602 megabytes. At 1137 times 8, I've got almost like 8 gigabytes of memory capacity.
No, I mean the DRAM. Since you said
the DRAM. That's the memory speed.
Right. Okay.
See, the thing is, I went from 2416 bytes to 1137 and 8 bytes. Not much difference because we have 8 gig and we're only transferring about 512 plus 76, only about 600 megabytes. So not much. In this case, the memory, as you keep adding more and more devices here and feed that to the memory, the performance will start changing. So for example, if I start doing this, I'm going to run this for sure.
I'm sorry. So Deepak, so the memory access is never a bottleneck.
Oh, it will be. It will be. It's just that right now in this particular model, it's not a bottleneck because I'm not sending enough data. But if I keep increasing it, like for example, wait, this is 200. I'll make it. So I'll make it 40. Okay. Oops. Then I'm going to reduce this even more. I'll make it 865. Okay. We're going to rerun it. I'm not running for 200 milliseconds. I'm only running it for like 40 milliseconds. So finish faster. You can see the spike right over here. There's some smaller spikes also now. So it's like you see a lot of smaller spikes as well. Let's see. This is at 878 things, so it's about 31% utilized. Let's see what's happening here. Okay, here we go. So what has happened now is the ARM, there's an overflow. Because here I'm sending this data in, but now because the DRAM is not able to handle the workload, I've got packet overflow right over here. So I've slowed down my DRAM. DRAM capacity is still high, but because the DRAM is slowed down, I'm starting to get overflows right over here.
Master, let's say master overflow. Overflow means
Reject. It's dropping the packet. It's dropping the request. It cannot.
reject.
Yeah, it's rejecting, dropping the requests. That's what's happening. Does that make sense, Jimmy?
Yes.
Yes.
Yeah.
Yes.
Yeah.
So what happens after the overflow?
You lost the data.
So it just skipped to that data, that
Yes.
packet, and then continue to the next packet.
See, typically what will end up happening is the buffer will be overwritten. So say there are 20 requests. The 21st request, right now they're all things. So what will happen is either if it's a higher priority, the buffer will be overwritten. If it's lower priority, it'll just be dropped.
I see.
Look at the buffer as just a FIFO, right? The first in, first out. So if I don't have any more space, I just have to drop it.
Okay.
Okay. So buffering is typically the biggest bottleneck. I mean, because you know exactly what is the, once you get access to the bus, you know exactly how much time it's going to take. Once you get access to DRAM, you know exactly how much time it's taking. But if you have to sit on a buffer here, or you have to sit on a buffer anywhere here, that's when you have the bottlenecks.
Okay. Can I see the buffer usage?
Yes. So here, for example, you can see like the master 4, buffer occupancy is 14 right over here. That's a read for the reads. If you notice over here for 5, which is the GPU, it's 2. And then it's 2 for I'm sorry, for the writes for the master 4, which is the ARM, the writes is 7, and no buffering for the master writes for GPU. Okay? But then if you look at the slave threshold, it has 3 and 3 on slave 1.
Yeah.
Slave 2 has no activity. No overhead. So yeah, so you can see that. Okay. So this is a very simple model that replaces a spreadsheet or an analytical design. Okay. Now, same design, but what we've done now is, so these are just more details I've written about them. I've said what are suggested some changes. Now, the same thing, but now I've modified it where I'm creating these regions. So, for certain amount of time, I have certain amount of data, then there is no activity. Then again, for certain amount of time, there is some data going. So I kind of have these interval-based traffic. Okay. So now I'm going to move into that type of a model. Yeah. So what is different is if you notice here, I have the range, minimum and maximum range, and I'm generating packets within that range. Same thing for CAN and Ethernet. But now for the ARM processing, I have a start time. Then I say, this is my interval. So in this case, my start time trigger rate is starts at 1 millisecond, and then my time between the reads. So there is like a range of about 50 nanoseconds. And during that 50 nanoseconds, the number of read tasks is 1,000. So within that 50 nanoseconds, I'm generating 1,000 requests. And of course, for a certain period of time, which is the trigger rate. Where's my trigger rate? Yeah, here we go. And then for 1 millisecond, there's no activity.
Mm-hmm.
So there is like 1 millisecond, no activity. Then for like, 50 nanoseconds is activity. Then nothing until for 1 millisecond, no activity. Then 50 nanoseconds is activity, and so on. So within those activity time period, there is, in this case, 1,000 packets or 1,000 requests. Okay.
Mm-hmm.
So same design, everything else is the same. If I go inside of this, let me check this because we made this change. Let me change these to right. And display, make any changes here. Display controller. Oh, sorry.
Mm.
So what I've done now is rather than just saying, like data comes and immediately sends it out, I've created a DMA here. Okay. So now it's, we have changed it to where earlier on it was, it was using the, it was just, like whatever came in immediately, it sent it out. But now we're using a real system. So we're adding a DMA block to it. Okay. So it'll give you, there's an additional delay associated with the processing that is now incorporated in here.
Mm.
Okay. So now, so essentially what this model does is it adds more accuracy to the request timing.
Mm-hmm.
It, it adds the display thing to become more of a DMA. It adds some of that functionality here. So when I go ahead and run it, now this one is obviously running a lot of data, but also the profile has changed a little bit over here. Because they're coming in bursts. And notice over here, you can see a spike over here. So even this one over here, the GPUs, notice the spike to the GPUs as well. So now as I keep adding, refining the model some more, the DMA, all of these different operations some more, I'm starting to get a more accurate picture of what's happening in my system. Oops, that's when 33 milliseconds showing up here. You can start seeing now it's not a fixed value. Like the ranges of these latencies is quite different. Most of these are fixed, but then you start seeing these ranges when many of them are interacting, you see the ranges are changing also. It doesn't need to run for so long. We can cut it right over here. I think I was trying to run it for much longer just to see if there's something interesting, but I think it becomes very symmetrical after some time. So only here there's some activity, but after that, so right over here at like 0.04, you can stop it. But this one has huge amount of data. The number of requests, everything is very significant in this model. Tom actually reminded me of something. You know, on the Axie bus, you can give higher priority to the GPU in the fixed priority array. So that way, what can happen is, you know, the latency will be high, will be lower for the GPU. I think I forgot that one. I'll write that up also. Okay, so now with this case, notice both 4 and 5 ARM and GPU there's a huge amount of data overflow. Utilization of the DRAM is very small, 1%, but I still have a huge overflow right over here. So when I look at the model, look at this. See, I've got these, you notice the other one had 20. I moved all of these to 5 right over here. And when I look at, where's my other graph? Here's my other graph. So notice over here, I reached my peak threshold for the slave. And you know, the peak read and write is over here. There's also for the slave 2, for the display, there's actually one over here as well. Okay. And notice over here for the, for master 4, it's, you know, which is the ARM, it's got a 4 for the read, 5 for the GPU. And then for the writes, master 1, 2, okay, let's look. Master 4, that's got a 5 for the writes. GPU has a 5 for the writes. So there was actually a lot of buffering for the writes as well in this model. And then you can see what the throughput is, number of IOs per second on the DMA block for the display controller. So it's 750 IOs per second. That's what's happening. This shows me what is my DRAM usage. It's so much, the throughput. And this tells me every device, how much of memory is it consuming. So notice the GPU, the DRAM throughput is so much megabytes per second, 701. But you can see how much the GPU and all these other ones are taking. You can see what the latency is across the DRAM as well. It shows you that details also. Now in this model, you can change those windows of operation. So you can have, you know, like a larger delay. So like, for example, here, the processing delay time, I can make it -7 here for the reads. So there's like, and then I can make this to be like 2500. I'm going to make this a little smaller. I'm going to make it 0.04. Go ahead and rerun it. I'll be right back in 1 minute, okay? Sorry about that. Thanks.
So, Tanaka-san,
Hi.
so is everything okay?
Yes. Yeah. Yeah.
Okay. Okay.
Yeah, but I needed to understand the text, the how to understand the text display, display. What it means. I need to understand
Text display messages.
yes, yeah.
Okay. Okay.
Yeah.
So, okay. So, so we have two different text display here, correct? And the one of them, like the one over there, which says, yeah, that one over there. This one is from the Axibus, and one is from the old system statistics. So the one from the Axibus will give you information about how the traffic is going through each master and each slave. So that will give an understanding on how the internals are working. So people who want to debug more onto that, we can use that statistics message. And on the other message, which is the system statistics, that will give information on how much memory was used by every master that came into that memory. So these are very useful statistics when we want to understand how the system works in overall. I think Debak is also back.
Yes, yes. Go ahead, Tom.
Okay. So if you look here on that message, on that system statistics, we can see how much memory was used by each master. So we can see
let
that.
me just make it bigger. There you go. Go ahead.
So we can see that DRAM memory used by underscore ARM processor, right? So there is ARM processor MP max, MP mean, MP mean minimum. So that will give an understanding of how much memory was used by ARM processor during this simulation period. Then we have the CAN, the memory used by CAN. So we can see how much memory was used by CAN in megabytes. So that is why there is some e-power, because it was just using 64 byte right at a time. So it didn't actually reach to a whole load level, but we can get that information also. Then when we look at the display controller, we can see it did almost around 0.00614 megabyte during the simulation time. Then for the Ethernet, we have the similar statistics. Then for the GPU, also similar statistics. So when we compare all of these statistics, we can see that the ARM processor was the one who used the memory the most, around 24.5 MB it used. So when we look at the total memory at the bottom, we can see DRAM memory used by total. That is a total. That is a total of 26 megabyte has been used, and of this 26 megabytes, the processor used 24 megabytes, and the remaining was only used by the rest of it, right? Then that is the memory statistics. Then at the bottom, we have the display controller statistics also. So since we are using the actual DMA controller in this model, we get detailed statistics for the display controller also. We can see how many IOs did the display controller did, what is the throughput for the display controller. All that statistics is also available at the bottom. So that is the overview of this text display. This text display will give that idea. So now we have, so is this text display clear? Is this okay?
Okay. Okay. This this example, the system starts in. Okay. For example, the ARM processor can be max and mean, and max and mean is but the same number.
Okay. So if we go to architecture setup and increase the sample size, right now we only have one sample during the simulation time. So if we increase the sample size, from there we will get more samples. So if I say 10 as the number of samples, then during the simulation time of 40 milliseconds, I will get 10 samples. So according to the sample count, the value calculated will be different. So we can get a more accurate view if the number of samples is high. So if we increase the number of samples to maybe 10 and run the simulation, then we can see a different, we can see a lot more samples. So more samples means more information at those instances of time. So we can see that how the max, mean are being changed over time according to the number of samples we are calculating.
What is the number of samples?
So, so let's say I am running the simulation for 40 milliseconds. Okay, and if the number of samples is 1, then we will calculate the statistics only for one time during the simulation. So that will happen at 40 milliseconds. Okay, so if the number of samples is 2, then I will calculate the statistics 2 times during the simulation, 2 times. So one at 20 milliseconds and one at 40 milliseconds. So now we have more data to get the statistics from. So then if I increase, now in this case, I have increased the statistics count to 10 count, correct? So every 10 milliseconds, every 4 milliseconds, I am calculating the statistics every 4 milliseconds. So that is how we can see that. So 4 milliseconds, we are getting one. Then 8 milliseconds. So we are getting more information, more system information.
Okay. This is a sampling time.
Sampling, yes, sampling time. Yes, exactly.
Okay, I understand. Okay, thank you. Okay.
So this is, do you understand everything on system stats? Everything okay?
Yes. Yeah.
Okay.
Yeah.
If you have any doubts, please tell me.
Okay. Good.
Okay. Now there is another text display which is obtained, which is having the information from Axibus. This only has information from Axibus. Okay. So what we have done is at the end of simulation at 40 milliseconds, it will print out details on what happened internally to the Axibus. Okay. So the first message will be about the overflow. So as Deepak mentioned before, each device, each master and slave has a threshold. Like it can be 2, 3, 10, 15. We can modify it. So if the threshold is reached and overflown, then that will be mentioned there, and which device was overflown. So we can see that the axi underscore 2, that is the best name. So axi underscore 2 underscore master 5. So that means the master 5 was overflown. So we can see the master 5 in this case is GPU, and the number of overflows is 576. So we understand that about 576 packets were rejected. Okay, so that is what the first part of it says. So it says that from master 5 of Axibus, axi underscore 2, about 576 packets were rejected out. Then the next statistics, that is the axi underscore 2 master 1. So the next part will give information about each device read and write throughput, how much megabytes was it done during the simulation. So we can see that master 1 write data Mbps about 0.1522. Then we can see that master 2 write data Mbps is about 0.008 Mbps. Then master 4 read data Mbps 596 Mbps, correct? And then for write data it is only 17 Mbps. So for each master and for each slave, that information is available. Okay, so we will get the information about how the this is the statistics generated internally for the Axie bus. So we get this information also. Now then we look at the third part, that will give whether the threshold was reached or not. What is the maximum threshold reached? So we can see that for Axie underscore 2 underscore slave 1. So for slave 1, the read threshold, the maximum of 5 was reached. So that is the maximum value that reached. And the number of transactions that went through this slave is 48,416. That many number of transactions went through for slave 1 read. Then on the next one, we have slave 1 write threshold. So read and write are separate channels, and so we are listing the statistics differently here. So write statistics and the read statistics different for each slave and each master. So we can see that for the write channel for this slave 1, that 1390, only about 1390 transactions went through for slave 1. That is for write, and the threshold is 5. Maximum threshold is 5. So similarly for the slave 2, that was for slave 1, and for slave 2 there is a write transaction of 12, and the threshold is only 1. So Tanaka-san, do you understand why the slave 2 is only having 12 transactions?
12?
Only 12 transactions. Do you understand why the slave 2 is being used only for 12 times?
Slave 2 is a display?
Yes.
Yeah, display controller.
Yeah, and it's only every 33 milliseconds, right?
Mm-hmm. Yes.
Slave 2. I don't know.
No, that's what every 33 milliseconds you're sending the request, and you're only running it for about 400 milliseconds. That's why.
What?
So the slave 2, which is where's my here, I'm going to minimize this. This one here, display, is only from the display controller. So during this time of 40 milliseconds, there's only 12 requests that have gone to the display controller. That's why it only shows 12. Only 12 transactions, that's all.
So the DMA controller will send the traffic in burst word sizes. So so there were about 12 bursts which was going to that display for write. So we only need to send write to the display. No need of read to the display. That is why there you can see slave to write usage, write threshold usage. There is no slave to read threshold usage because we are not doing any read from the display, correct? So we can see that information here. So this statistics over here can be used to understand what is happening in the Axie, how the master and the slave is communicating, whether there is any unexpected behavior like any dropping of packet. In this case, there is an overflow. So we can understand all those details by looking at this text display. Does it make sense, Tanaka-san?
I think it is difficult for me.
Okay.
Oh, it's Tanaka-san. Think about it this way.
Yeah.
You know, when you do in the first model, when we said the data size was 6,000 bytes, right? We sent all 6,000 bytes. We're sending to the display.
Okay.
We sent all 6,000 bytes in one shot. So like one packet.
Okay.
Now, with this model, we have added a DMA, which is more of a hardware device.
Okay.
It's not part of Drive PX, it's outside. Okay. So now when we added that, the DMA cannot send 6,000 in one shot. It has certain thing, like for example, you can only send 512 bytes every time.
Okay.
It sends 512 bytes, gets acknowledgement, 512 bytes, gets acknowledgement, 512 bytes, gets acknowledgement. So there are 12 times it has to send 512 to get 6,114.
Okay, 12 times is the bus cycle occurs.
Yes, exactly. Bus cycle and update for the DMA. So that's how you get the 12.
Okay, good.
So that's how it works.
Yeah. Yes. Okay.
Okay. So now there's another model that we have built. So this is the second model. So the difference is the traffic for the ARM and GPU, they've changed. It's a different traffic block. And then this one has a DMA. Two differences. The third model, which is this one over here. Okay. This model now is going to hardware. Okay. Here what we have is, we have all of these are now back to using the old traffic generator, just the GPU rate, the ARM rate, things like that. But when I go inside of this, I'm implementing the Drive PX completely. The full hardware implementation of Drive PX. Okay. Now this is the hardware. What does the user change? The user changes this information. That is the list of tasks that are going to execute on those processor models. Okay. So this is the more detailed version. I don't know if you want to do it today. Maybe like let the customer try the first two models, then we can do this model for them.
Yeah. Okay. Yeah.
But so this is the flow. The the ARM is getting triggered. You have the flow, and then this one here maps it to one of these processors or one of these processors. Okay, I'm just going to go ahead and run it so you can see the difference. Now there are some differences over here now, because now we have, like, this is the all the GPU processing. This is showing me the power consumption on the GPU. This shows the bus latencies, but now the bus latency, you can see the ARM72, core 3, core 4, core 1. You can see A72, Denver 1, Denver 2. So you can now start seeing the individual processors, individual processor cores. Okay.
Yeah.
So it's a little different model from the earlier ones, because now we have it all split up as individual cores, and we have some software profile that's running on each of the cores.
Okay. Yeah.
Okay. So it's a more it starts becoming a more detailed model. So you can see that's the Ethernet traffic going here, and then you can see all the latency. This is what these two processors, what they call the ARM. I'm sorry, GPU, the latency is quite high now, because now it's no longer just like a read and write request. Now we have the detailed GPU implementation inside. Okay. So this starts becoming a very detailed model of the system. So now when I look at this, you can see what's my DRAM utilization. Then I can see, like, for example, here, the important ones are, let me go up to one of them over here. Okay. So if you look at like this one here, you can see what the pipeline utilization is. You can see what the iCache and Dcache, in this case, there's no Dcache activity, but you can see what the iCache activity is. You can also see, what the L2 utilization, in this case, there's no L2, but yeah, here we go. You can see what the DRAM usage now is. So everything changes. You start getting more detailed statistics on the model. So compared to the previous one, this is a very different model. So this is another type of a model that we have created. Now, this one here is more hardware centric. So we've created another variation of the model. This is what I was showing you earlier. In this case, the user does not modify anything over here except maybe the DRAM speed. But here now, he focuses on only his application. So you can have any number of applications and you can specify these applications. Like for example, over here, I'm going to the Denver one. Here I can specify I'm going to A72 one. Then right here, I'm saying, I don't care. I'm going to either 1 or 2. While here, I'm going to any one of these 4 cores. So there's a number here, generating random numbers. So these are all going to different processor cores. And this one here is going to the GPU. This one here is going to the display. Okay.
Yeah.
So now this flow here is more, it's like the traffic model, but now we have more detailed definition of what exactly is happening through the system. You know, when it happens, what happens before, what happens after, all of those are taken into consideration. So you start with a traffic model, get burst traffic, you do a simple hardware model, and now we're doing a pure analysis, more detailed analysis of what your software can do.
Yeah. Okay.
Right? So it's the next level.
Yeah.
Okay.
Yeah, it looks good because just started at the basic model and yes, customer can maybe I hope the customer can understand the basic is a very simple model to the and the detailed model. Okay. Hello?
Yes.
Okay.
Okay. So the latest install has all of these models, but I think if you don't have the latest install, I will email these models to you so you can try to do some experiments with it. Okay.
Yeah. Sorry, in Japanese?
Yes, sure.
小島さん。
はい。はい。
わかりました？
なんとなくは、はい、わかります。
まあ、そうですね。どこまでどうやってパナソニックに見せるかっていうのはあるんだけど、なんて言うんだろう。パラメータ変えればこう変わりますよっていうシンプルなやつから、最後は、命令が載ってるのまで来てるけど。
そうですね、はい。
ちょっとうちの方でだからですね、もう少しこう、パラメータ変えると、何がどう影響するのかっていうと、あと見方ですよね。どうやって見るのかっていうのを。あれすればなんか、それなりに説明はできそうな気がするな。
そ そうですね。
どこですか？
細かいところはあんまりよくわからないんですけど、
うん。
まあ、大まかなところはわかりますんで、大体は。
うん。まあ、大体3つのモデル作ってくれて、まあ、大体、まあ、分かったので、まあ、あれかな。
見てみてっていう感じですかね。
まあ、だからちょっと一回自分でパラメータをちょっと変えてみて、
はい。
で、ちょっと触ってみて、それであとはですね、パナソニックに一回、
そうですね。はい。
うん、見せてあげるのがいいかなと思いますね。
はい。そうですね。
うん。はい。Deepak and Jimmy,
Yes.
Tom, yeah, thank you very much. Yeah, I think we can understand the three models.
Oh, excellent.
Okay.
Good.
So what I'll do is I will send you the presentation, Tanaka-san, and I'll also send you these 3 models to look at.
Okay, please.
4 models. Okay, I'll send that to you right now.
Okay, and after that we will try to use your 3 platform models, and we have to understand the more deeply, and we will demo to the Panasonic. Okay, and yeah, I hope they can understand what is a mirabilis too.
Right.
Yeah, I hope, and they are going to evaluate your tool. Okay.
Okay.
I hope. Okay.
So what do they need to understand to evaluate the tool? Is there any particular areas that they want to focus on? Have they given us any information as to what they want to do in the evaluation?
I say evaluation means okay, they requested to see the they want to see the bus traffic and some delays and the latency. They want to see that, and I think yeah, and they want to change some parameters by themselves. Okay.
Okay.
Yeah, and they want evaluate easy to use. One item is easy to use. Change the parameter and can see the result. Yeah.
Okay.
It is a fast evaluation, but because currently they are using a spreadsheet. Okay.
Okay.
Therefore, it is the mirabilis tool has a value. So has a value than the spreadsheet. This is the first priority. Okay.
Okay.
Yeah.
Are they looking at any other software, or is it only Mirabilis?
Sorry?
Are they looking at any other software, or is it only Mirabilis they're looking at?
Currently, I think only Mirabilis.
Okay.
Yeah.
Okay. And the ease of use, looking at bus traffic and the where they can start up by themselves, that is their main goal, right? Right now.
Yeah.
Okay, good.
Okay. Bus arbitration, bus congestion.
Okay.
is that they said they want to see the display frame rate. Frame rate means maybe sometimes is a bus transaction is very busy and data cannot go to the display.
Okay.
And they want to see enough frame rate. Maybe, I think.
Okay. Okay. Yeah, that must make sense.
Okay. Yeah. Yeah. Maybe yeah. They want to change the many parameters, I think. Okay. Yeah. Thank you very much. Okay.
Tanaka-san, once you talk to Panasonic, if you have anything that you want to show them, but we didn't cover it today, please
okay.
Let us know. We can sit down together and figure out how to demo the feature or the function that Panasonic want to look at.
Oh, okay, thank you very much.
Yeah.
Awesome.
Thank you.
And I sent you 2 emails, Tanaka-san. Take a look at those and let me know if you have any questions.
Oh, okay. Okay.
Cool. Okay.
Thank
you very much. Bye.
Thank you.
Thank
you
you,
so much.
Tanaka-san. Thank you, Simbo-san and Kojima-san.
Thank you very much.
Thank you.
Yep.
Bye.